This is a kinematics example problem of a simultaneous solution. Here's our example problem. A car is traveling at 80 kilometers per hour in a 50 kilometer per hour zone when it passes a stationary police motorcycle. The police motorcycle begins chasing the car immediately, accelerating at a constant 8.0 meters per second squared. Assuming the car never changes its motion, how much time does it take the police motorcycle to catch up to the car, and how much distance does the motorcycle cover during the chase? Looking at this problem, there's a story about a speeding car and a police motorcycle. What's really going on is there are two objects. One moves at a constant speed, which is 80 kilometers per hour. This 50 kilometer per hour thing, that's not really important. That's just background to the story. We're not even going to use that number. So one object travels at a constant 80 kilometers per hour. The other object begins at rest, says it's stationary to begin with, and then accelerates at 8.0 meters per second squared through the entire story. The question is asking us to find a special point, the catch point, the intercept point, when the object that was traveling at a constant speed is at the same location at the same time as the object that began at rest but has been accelerating constantly. Let's start by using a position versus time graph to organize our thinking about this problem. The object that's moving at a constant speed, the car that's going 80 kilometers per hour, a constant speed means that the displacement changes by the same amount for every equal time interval. This is going to be a line with constant slope. It's going to look something like that on our graph. The police motorcycle starts at rest. Being at rest on a position versus time plot is a horizontal line, but this line isn't going to stay horizontal because the police motorcycle is going to keep speeding up and speeding up and speeding up. It's constantly accelerating. As its velocity is constantly increasing, the slope of the line is constantly increasing. This is going to be a curve. I'm not sure I can draw a super smooth curve using the tools I have here, but this is what I've got. I've drawn them up to the intercept point, the intersection point. This point is where the police motorcycle and the speeding car meet up at the same position at the same time. This is the point we're solving for. And in order to solve this problem, we are definitely going to need to organize the variables that were given to us in the problem and to consider the unknowns that we're looking for. We have two objects, so there's a lot going on here. Let's start thinking about the car. So the car definitely has an initial position. I'm going to call it X, C, I, and we're going to call that 0. There's also an XCF, final position of the car, and that is unknown. That's one of the things we're actually going to solve for. This final position, the final event, is that intercept. There's our initial time, which isn't unique to the car, so that's just an initial time. It begins at 0, and then our final time, again, that's something that we are going to solve for. That's the intercept time. For the car has a constant velocity, so the initial and the final are the same. Now this time, I need to extract a number from the problem. The problem listed the car's speed as 80 kilometers per hour. But then the police motorcycle had different units. It had an acceleration of 8.0 meters per second squared. I need those units to match. They need to both be same distance units, and they both need to be the same time units. I'm going to choose to convert the car's speed from kilometers per hour into meters per second. In order to do that, I'm going to multiply by 1,000 meters per kilometer and divide by 3,600 seconds in an hour. And my final result is going to be 22.2 meters per second for the car's speed. Let me kind of circle that off there. So this is pretty much all that I know about the car. Now the motorcycle, it's all right with you to save space. I'm going to call it a bike. It is going to have the same initial position. That'll be an XB initial, also 0. And then the XB final is unknown, but XB final is the same as XC final because they end in the same position. And so let me write that down in kind of a special way so that it's really noticeable. XCF is going to be the same as XBF. All right. Now the times, again, I have an initial, that's 0, and then a final time, which is unknown, but once again, the final time of the bike is the same as the final time of the car. In fact, those didn't even have subscripts. They were already set up to be the same. It's the same unit. All right. Finally, the bike has an initial velocity that's 0 and a final velocity that I do not know at this time, and an acceleration of the bike that is 8. I'm going to save a little space. I'm not going to write the 0.0. 8 meters per second squared. All right, that's a little bit untidy, but that's me trying to organize my variables. Now it's time to start thinking about equations for this problem. I've written out 3 kinematics equations so that I can take a look at them and try to decide what's going to be the most useful. This first one involves acceleration, a displacement, an initial velocity. That sounds pretty good. But then it's solving for a final velocity, which could be useful, but I don't really think that's what I'm after. And so I do not think this is the equation I want. Let me take a look at this second one. It's real similar. Instead of looking at displacement, though, it's looking at if I know a change in time and the acceleration, I can calculate a final velocity. Again, I'm just not really sure that that's what I'm looking for. This last one looks the most promising to me because it has both change in time, and with the x final and the x initial, I can actually rewrite this as a delta x. If I subtract off the x initial from both sides, this becomes delta x equals v initial times delta t plus 1/2 a delta t squared. In my list of variables that I made before, I had delta x's because I had x finals and x initials. I had delta t's because I had t initials and t finals. I had an initial velocity. I had an acceleration. I think this is going to be the one that I'm going to try to use. All right, using the equation that I selected, let me take a look at how that's going to look for the car. I have a delta x for the car. Although in this problem there's only one delta x since they're going to have the same displacement if I'm following them just to that intercept point. And then this is going to be equal to that v initial times delta t. And then I could add the 1/2 at squared, but there's no acceleration for the car. That part's going to be 0. So this is all I've got for the car. I can go ahead and fill in the one number I have, and that is going to be 22.2 meters per second times delta t. All right, so then let's take a look at the bike, the motorcycle, the police motorcycle. There's also a delta t, a delta x in this problem. And then this time the v initial for the motorcycle, for the bike, is 0. And so I'm not even going to write that down. That's not going to matter. So I can skip straight to the 1/2 a delta t squared. Now I can go ahead and put in, again, the one number I have. The acceleration for the bike is 8.0 meters per second squared. I've got 1/2 of that So this is going to come out to be 4.0 meters per second squared, all times delta t squared. Alright, I had set up a dividing line so that I could organize my car information and my bike information. Now it's time to put them together. I have two unknowns in each equation, but I have two equations. I'm going to do something called a simultaneous solution. I can solve for these two things kind of at the same time. And here's how it's going to look. Delta x for the car is exactly the same thing as delta x for the bike, which means I can connect the parts of the equations that have numbers on them, the parts that are to the right of the equal sign, I can connect those together. So 22.2 meters per second times delta t, that's equal to delta x, so it's also equal to 4.0 meters per second squared times delta t squared. Alright, to complete the math on this, I'm going to divide both sides by the 4.0 meters per second squared. And I'm also going to divide both sides by a delta t. So now, let me switch colors so you can see a little more clearly. The delta t's are going to cancel out here. The 4's are going to cancel. And there's a delta t here which is going to wipe out the squared. So here's what I'm left with. 22.2 divided by 4.0 is going to be 5.5 seconds equals, all that I'm left with over here on the right-hand side is the delta t. Great, so I've solved for the time. That was one step of what I needed to do. And again, my handwriting is pretty bad. I'm doing these on my iPad, but that's 5.5 seconds over here equals delta t. I also needed to get delta x. Well, I've got an equation that once I know delta t will very easily give me delta x right up here. So I can go ahead and substitute in the 5.5 seconds for delta t, and you can check me, but I think we will find that, oops, I'd really rather have this in black. I think we'll find that the delta x is going to be 123 meters. So we have solved both things that the question asked us for, both how long does it take in terms of time and what is the distance that the chase takes. 123 meters. A meter is pretty close to a yard. 123 yards. That's going to be almost 1 1/3 football fields, since a meter is a little bit longer than a yard. And so I'm thinking for this scenario where 22.2 meters per second is pretty close to 50 miles an hour, this seems reasonable. The 8.0 meters per second squared acceleration on the bike is pretty high. That bike's going to speed up pretty fast, and it's just going to go, 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 go. Just a little bit unrealistic. But in terms of checking my answers, it's not way off, even if it's a little bit of an unrealistic scenario. These numbers seem okay to me.